Alright, this is the introduction for the lab on momentum and collisions, and what we're essentially going to be doing is we're going to be colliding some carts, doing some collisions, and we're going to observe the velocity of a cart, of two carts actually, and we're going to calculate their momentum, we're going to calculate their energy. The whole point of this particular lab is to observe elastic collisions, and elastic collisions have the property where both momentum and the energy are going to be conserved. For inelastic collisions, the momentum is going to be conserved, but energy is going to be lost. So here's what we need. We need the standard vernier interface with Logger Pro. We need two motion detectors this time. We need the dynamics track, two carts. We need a mass to increase the mass of one of the carts, and not shown, we do need a level. Don't forget this pre-lab question. I know I've kind of scribbled over it, but please make sure you go ahead and do this before the lab. So what you're going to do is you're going to attach the motion detectors and put them against the track. I don't use the brackets, I just set them on there, and I'll show you a picture of what that looks like in a little bit. And you're going to make sure that they're both on the track setting. You're going to mess around with some of the data collection thing, and very, very, very important is you do want to make sure you level these things. Momentum is only going to be conserved in the absence of external forces, and I don't want gravity messing with this experiment. You're going to measure the mass of each of the two carts. One thing I want to mention is when you grab the two carts, there's going to be magnets on one side and Velcro on the other side. We're going to use both the magnets and the Velcro. Make sure you grab one with Velcro hooks and one with Velcro loops. That'll be important when we do the inelastic collisions. Now what you're going to do is you're going to make sure that the carts have the magnets facing each other, and you're going to place them on the track. First thing we need to do is we need to make sure that they're looking both in the same direction. And very typically, this motion detector is going to be looking in that direction. It's going to call that direction positive. This one's going to be looking in that direction. It's going to call that direction positive. And when it comes to momentum, it's a vector quantity. And we want both of these guys to be calling the same direction positive. So what I want you to do is to say, hey, this motion detector right there, call that direction positive. But we need to make sure that they actually are calling away from them positive. Very typically that's what happens, but once in a while you plug these things in and something funky happens. So let's talk about how we're going to do that. First though, I want to show you what the setup looks like, or in reality versus the cartoon. So here's the motion detector number 1, here's my motion detector number 1. Again, I don't use the brackets, I just kind of set them on there. Motion detector number 2, motion detector number 2. And here we have the two carts. Again, you definitely want to make sure that these things are perfectly level. The bubble levels will get you kind of close. After you get kind of close, go ahead and give it a push in one direction, give it a push in the other direction, and if the carts preferentially go in one direction versus the other, kind of do some fine-tuning. Now what you're going to do to ensure that they're looking in the same direction is you're going to take two of the carts, or just one of the carts, and you're going to wiggle it back and forth, back and forth, back and forth, and you're going to take a look at the velocity versus time graph. One of the carts is most likely going to be blue, so that cart's going to be going kind of like that, or that's going to be motion detector number 1. And motion detector number 2 is going to usually be a red color, and if these guys are looking in the opposite directions, then they're going to be mirror images of each other, so that would be number 2. If this is the case, then what you're going to do is you're going to just reverse one of those two, it doesn't really matter which one, and you want these guys to line up perfectly on top of each other. So you're going to reverse one of them and then wiggle it back and forth, and it should look a whole awful lot like this. This is what you want. Then what we're going to do is we're going to do some collisions, and you want to make sure the carts are not too awful close to the motion detectors because they are blind if you get too close to them. You're going to go ahead and start the data collection, and then you're going to push one of the carts towards the other one. So initially one of the carts is going to be at rest and the other one is going to be moving towards it. You're going to use the Control E button, use the examine tool, and read the initial and final velocities of each cart before and after the collision occurred. So let me show you what that looks like. So this is what this is going to look like. We're going to have two carts, we're going to have the same mass, and what we're going to do is we're going to have this cart initially at rest, this cart's going to go towards it. Perfect. Now what we can do is we can look at the velocity versus time for these guys. And what we're going to see is one of the carts is going to be coming in, and then it's going to collide with the other cart. That collision does take a little bit of time, and it's probably going to have no velocity whatsoever. Then we're going to have the other cart, and the other cart is going to be sitting there. It's going to acquire some of that velocity, and in the perfect world, it's going to look kind of like that. You're going to use the examine tool. You're going to read off that velocity, and you're going to read off that velocity. You're going to ignore this little slice of heaven in the middle, and you're going to record that velocity, and you're going to record that velocity. Now, you want to go as close to the collision as possible, because the reality is there is some friction here, so this velocity is actually going to be getting smaller, and this velocity actually kind of started off way up there. Just stick as close as you can to the collision. One thing I will note is if your graph doesn't look like this, if it looks like it's flipped over, then just push the carts in the other direction. So where are you going to record this? Well, you're going to record this right there. You're going to have cart number 1, you're going to have the mass. Cart number 2, you're going to have the mass. You're going to record the initial velocity and final velocity of cart number 1. That would be like the red one. And then cart number 2, you would record the initial velocity and the final velocity. You're actually going to do 2 more runs with the magnets. So let's talk about those 2 guys right there. For run number 2, I want you to have the carts with the same mass, and you're going to push the carts towards each other. Please try to ensure that the velocities are not the same, because if the velocities are the same, you would have virtually no momentum in the system before, no momentum in the system afterwards, and trying to measure 0 is very, very, very hard. Run number 2 is the one that might give you some problems. For run number 3, what I want you to do is increase the mass of one of the 2 carts, and you can do it for either of the carts, it really don't matter, and then you're going to essentially repeat run number 1 again. When it comes to increasing the mass of the carts, I have these masses that are going to be in the front of the room, and I do have some fancy brackets, but what I found is tape works pretty well for this. Much like with run number 1, you already know the masses of the cart, so those actually aren't going to change. Well, it will change for one of these 2. And you're just going to use the examine button, Control E, read off initial velocity final, initial and final. For these calculations, you can do that afterwards on your own. So you can do that on your own, you can do that on your own, you can do that on your own. And I do have something to speed you up when you get to that part. What we're going to do is we're going to also calculate the energy, and this is something that you can do on your own. Energy is going to be 1/2 mass velocity squared, and just for the record, momentum is going to be mass multiplied by velocity. We do have to pay attention to negative signs when we're doing momentum. Momentum can be positive or negative. We are going to calculate the ratio of the momentum before and afterwards, and if this number is close to 1, then momentum was conserved, and it should be close to 1. It's probably going to be, in the 0.9-ish range for this lab, because we do have a little bit of friction. The ratio of energy in elastic collisions, it should be close to 1, and indeed it is. It's in the 0.8, 0.9-ish range. You can do these all on your own afterwards. What I want you to do is to jump down and do the experiment for inelastic collisions. For inelastic collisions, you're going to turn them such that the Velcro sides are facing each other. And Velcro to Velcro, not magnet to Velcro. Please don't do that. You're going to do 3 runs, run 1, run 2, and run 3, and things are going to look very similar to what we did for elastic collisions. For inelastic collisions, for run number 1, what I want you to do is I want you to go ahead and have the carts with the same mass facing each other. Cart 1 is going to be moving, cart 2 is going to be at rest, and it's probably going to look something like this. And notice how they stuck together. What you're going to do is you're just going to use the examine button, Control E, read those velocities off, and record them in the data table. What you're going to do is you're going to do the same thing. Run number 1 is going to be the same mass, 1 cart moving, 1 cart at rest. Run number 2, both carts moving, trying not to get them at the same velocity. In run number 3, you're going to increase the mass of one of the 2 carts, have one of them at rest and the other one moving. Again, you're just going to read off the velocities, you're going to record them, you're going to record them, or you're going to record them. All of this can be done afterwards, and all of this can be done afterwards. Now, I do have something to speed you up. I have an Excel spreadsheet that's going to let you go ahead and input the velocities, and you can then go ahead and put everything in. And let me just go ahead and get some numbers in right here. You can kind of see that everything is kind of populating. Right here I've inputted just some random masses. I'll go ahead and put 0.5 and 0.5 in there. You can see everything kind of updating. And if I had cart number 1 coming in at a perfect velocity of 1 meters per second, leaving with nothing, cart number 2 has the same mass initially at rest, and it picks up all of that, you can kind of see that this thing has already done the calculation for me. Because I chose everything to be perfect, the ratio is 1, and the ratio is 1. So you can actually use this to fill out your tables, but I do want to see one sample calculation when it comes to that. So when you're way up here and it says, show a calculation, please do show me one sample calculation, and you can use the spreadsheet to check you. But I do want to, for you to show me that you know what the spreadsheet's doing. It's not just some black box.